April 3rd, 1943, Republic Aviation Airfield, Farmingdale, New York. A cold wind rolls across the runway. A P-47 Thunderbolt crouches at the edge of the tarmac, its aluminum skin catching the morning sun. Mechanics step back as the ignition sequence begins. The Pratt & Whitney R2800 roars awake, a deep, rolling growl that swells into a deafening thunder. Dust and exhaust swirl in the prop wash, filling the air with the sharp smell of oil and burning fuel. The propeller spins faster and faster, first a blur, then a solid disc. But behind the spectacle, the men watching know something's wrong. The powerful engine strains against the limitations of the narrow propeller blades. It's like trying to funnel a river through a straw. The aircraft can fly, but not as fast as it should. At high altitude, the problem becomes a wall. Thrust falters, speed bleeds away. The world's most powerful piston engines are being held back by their own propellers. And somewhere in a quiet engineering office, a man sketches a design that seems absurd. A blade fatter, wider, almost like a paddle. Soon, that sketch will change everything. By the spring of 1943, the Second World War had become a contest of industrial endurance and technological speed. The skies above Europe were increasingly decisive. If the Allies could seize and hold air superiority, the Axis war machine would suffocate beneath the weight of its own vulnerability. Every bomber raid, every fighter escort, every interception depended on a single element: speed and altitude. The United States Army Air Forces were ramping up their daylight bombing campaigns deep into occupied Europe. B-17 Flying Fortresses and B-24 Liberators took to the sky in massive, tight formations. But to survive against the Luftwaffe, they needed fighter protection. High-altitude escort fighters became more than just useful. They became a necessity. In this race for supremacy, aircraft like the P-47 Thunderbolt emerged as powerful but flawed tools. The Thunderbolt carried one of the most formidable engines ever fitted to a fighter aircraft, the Pratt & Whitney R2800 Double Wasp, producing nearly 2,000 horsepower. It was an engineering marvel, but at high altitudes where bomber formations flew, it was hamstrung by a bottleneck no one could ignore: its propeller. The Thunderbolt's original propeller used a traditional narrow blade design inherited from the early days of high-speed flight. At lower speeds, it performed adequately. But as the Thunderbolt climbed above 20,000 feet and pushed toward the transonic range at the blade tips, compressibility effects set in. Airflow around the blades became turbulent, efficiency plummeted, and the propeller struggled to translate engine power into thrust. It wasn't just the Thunderbolt. Across the Allied fleet, similar problems were emerging. More powerful engines were being produced at a breathtaking pace, but the technology to fully use that power lagged behind. The blade designs that worked in the 1930s were suddenly inadequate for the new generation of warplanes. Commanders saw the symptoms: climb rates below expectations, sluggish acceleration, and an inability to match the speeds theoretically possible on paper. Fighter pilots noticed it too. At high altitude, the aircraft felt heavy, slow to respond, laboring to gain speed in a fight where seconds could mean life or death. Meanwhile, the war was accelerating. By 1943, Luftwaffe fighters like the Bf-109G and the FW-190A dominated the mid to high altitude band over Western Europe. They could climb faster, strike bomber formations, and break away before Allied escorts could catch them. This imbalance threatened the strategic bombing campaign itself. The US response was not to slow down, but to push harder. New engines were pushed toward their limits. Boost pressures increased. Superchargers roared. But no matter how powerful the engine, the bottleneck remained at the front: the propeller. Every extra horsepower wasted was an opportunity lost. In the halls of engineering firms like Hamilton Standard, the problem became a mission. If the Allies were to compete in this new aerial environment, they needed a way to convert brute force into usable thrust at altitude. They needed a propeller that could grab the air more effectively without becoming inefficient or dangerous as tip speeds approached the speed of sound. That search would lead to one of the most important and initially ridiculed engineering solutions of the entire air war. The idea came not from a famous general or a celebrated pilot, but from a quiet, methodical engineer who believed the answer lay in reshaping the blades themselves. His name was Frank Walker Caldwell. To the average serviceman, he was just another engineer in a shirt and tie. But inside the headquarters of Hamilton Standard Propellers, Caldwell was already something of a legend. A methodical, relentless innovator, he had spent the 1930s pioneering the constant speed propeller, technology that had quietly transformed aircraft performance before the war ever began. By 1943, Caldwell faced a new frontier. The world's most powerful piston engines were pushing against the physical limits of conventional propeller design. Fighter aircraft like the P-47 Thunderbolt and later the P-51 Mustang had outgrown the slender, elegant blades of the pre-war era. What had once been efficient now became an obstacle. The problem was physics itself. As engines grew stronger, propeller tips approached supersonic speeds in level flight. At these high rotational velocities, compressibility effects set in. Shock waves formed at the leading edges, drag skyrocketed, and thrust collapsed. Engine power was wasted trying to force air around a shape that simply wasn't built for it. The very weapon meant to make these fighters dominant, their engines, was shackled by their blades. Caldwell's solution was as radical as it was simple. If the old propellers sliced the air like knives, perhaps the new ones needed to push it like paddles. Instead of the thin, tapered blades of the 1930s, Caldwell sketched designs with wide chords and thick roots, distributing the load more evenly across the blade. The concept would allow more of the engine's power to be transferred into thrust, especially at high altitudes where air density fell. But the design looked strange. To pilots accustomed to slim, elegant props, Caldwell's wide blades looked clumsy, almost agricultural. Mechanics joked that they belonged on a boat, not on a fighter aircraft. And yet, early calculations told another story. Increased thrust, improved climb rate, and most importantly, sustained speed above 25,000 feet. Caldwell's team at Hamilton Standard refined the design, creating what would become known as the paddle blade propeller. Its defining feature was a broader blade with a carefully engineered twist, optimized to maintain efficiency as the aircraft climbed and accelerated. To counteract the increased aerodynamic loads, the hub and pitch control systems were reinforced, ensuring the propeller could withstand the full output of engines like the R2800. The first prototypes were mounted on test airframes. In the spring of 1943, Thunderbolts fitted with paddle blade propellers began their trials. Engineers watched as the aircraft accelerated more cleanly, climbed more eagerly, and sustained speed where standard blades faltered. Instrument panels told the story clearly. Hundreds of additional horsepower were finally reaching the air. But the leap wasn't just mechanical, it was strategic. The United States Army Air Forces understood that any improvement in climb rate and top speed would directly affect survival rates over Europe. A fighter that could catch or outrun its opponent didn't just protect itself, it protected entire bomber formations. Skepticism gave way to urgency. The Army authorized large-scale retrofitting of P-47s with paddle blade propellers, and Hamilton Standard's factories began working around the clock. Every new blade that rolled off the line brought the Allies a step closer to matching and eventually surpassing Luftwaffe performance at high altitude. What had started as a crazy sketch on Caldwell's drafting table was now about to reshape the air war over Europe. And soon it would be tested not in wind tunnels, but in combat. When the first P-47s arrived at test airfields fitted with the new paddle blade propellers, the reaction among many pilots was not excitement, but unease. The wide, paddle-like blades looked bulky and strange. Fighter pilots of the early 1940s were used to narrow, elegant props, clean lines that looked fast. These new blades, by contrast, seemed heavy, even wrong. Veteran pilots walked around the aircraft slowly, running their hands along the blunt edges. Some muttered that the added drag would slow them down, not speed them up. To them, it was a radical break from what a high-performance fighter should look like. And yet, when the engines fired and the aircraft left the runway, doubt began to fade. On climb-out, the difference was immediate. Pilots accustomed to watching their thunderbolts labor into the sky felt the nose lift more eagerly. At altitude, where the old blades faltered, these new ones kept pulling. The speedometer climbed higher, the engine responded cleaner. As the first test flights landed, the same pilots who had doubted the design began quietly asking when their squadrons would be equipped. Beneath the skepticism lay something very human: fear of the unfamiliar. But in war, results speak louder than appearances. The strategic bombing offensive over Germany relied on long-range escort fighters. In 1943, Thunderbolts struggled to climb fast enough to intercept enemy fighters before they reached the bombers. Luftwaffe, Bf-109s and Fw-190s could attack from above, diving down with the advantage of altitude and speed. The old narrow blade props simply couldn't deliver the performance needed at operational altitudes. The paddle blade changed the equation. Suddenly, Thunderbolts were reaching bomber formations faster, climbing with purpose, and intercepting enemy aircraft where the fight began, not after the damage was done. Speed increased by more than 25 mph at altitude, and climb rates improved dramatically. In tactical terms, this wasn't just a number on paper. It shifted initiative. Now, American escorts could meet the Luftwaffe head-on. Bomber formations that once braced for incoming German attacks at 25,000 feet now had fighter cover already in place. Tactical doctrine adapted almost overnight. Squadrons could launch later, catch up faster, and stay in formation longer. For bomber crews flying into the heart of German defenses, the difference was life and death. Technically, the genius of Caldwell's design lay in understanding airflow at the edge of the speed envelope. As the tips of conventional blades neared Mach 1, drag increased exponentially, robbing the propeller of efficiency. The paddle blades solved this through two critical innovations: wider chord and optimized twist. By distributing aerodynamic load across a broader area, the paddle blade allowed the aircraft to convert more engine power into thrust without pushing the tips into critical speed regions too quickly. The increased surface area acted like a more efficient lever, giving each revolution more bite on the air. This was complemented by precise variable pitch control, technology Caldwell himself had helped perfect years earlier. The result was a propeller that delivered more thrust, especially where it mattered most, during sustained climbs and high-altitude cruise. The technology wasn't glamorous. It didn't produce the raw spectacle of a bigger engine or a new airframe. But in engineering, sometimes the most decisive, advantages are quiet. They live in shapes, angles, and forces invisible to the naked eye. And this quiet innovation would ripple far beyond a single aircraft type. The winter sky was hard and clear, the kind of cold that sharpened every sound. On the flight line, rows of P-47 Thunderbolts sat poised, their canopies glinting in the weak sun. Ground crews hurried between aircraft, fastening panels, checking superchargers, tightening harnesses. Inside the cockpits, engines rumbled, deep, confident, almost alive. But these weren't the same Thunderbolts that had struggled the previous year. Beneath their massive noses, Hamilton Standard paddle blade propellers turned slowly in the icy air. Broad, powerful, unmistakable. As the first flight roared down the runway, the difference was immediate. Acceleration came fast, smooth, with less hesitation. By the end of the strip, the aircraft leapt skyward. Pilots who had spent months coaxing their machines into the climb suddenly found themselves pulled upward. At 25,000 feet, where older props began to starve the engine of usable thrust, the paddle blades bit deeper, holding speed steady where it used to fall. This was the operational debut of the paddle blade Thunderbolt, and it happened not in tests or training, but on a bomber escort mission deep into Germany. The 8th Air Force was striking aircraft production centers, prime targets for the Luftwaffe. As the formation approached the German border, radar stations lit up. Jagdgeschwader squadrons scrambled to intercept. The Luftwaffe expected to face the same Thunderbolts they had toyed with months earlier. What they met, instead, was something entirely different. Climbing at speeds once unthinkable, the escorting fighters reached altitude in formation with the bombers. No delays, no lagging behind. For the first time, American fighters were arriving in the fight on time. German Bf-109Gs dove from above, but this time, Thunderbolts met them head-on, not from below. Dogfights erupted high over the Ruhr, and in those few decisive minutes, the hidden advantage of the paddle blade showed its teeth. The Thunderbolts matched the German fighters in climb. They maintained speed in the thin, freezing air. They could stay in the fight. One pilot from the 56th Fighter Group described the sensation in a later report. "It was like flying a different airplane. We used to level out and lose speed up there. Not anymore." For the Luftwaffe, accustomed to dictating the terms of engagement at altitude, this was a shock. Their edge was eroding, and fast. That day's mission wasn't just another escort. It was a signal, quiet but unmistakable, that the balance of power in the air was shifting. And it was shifting blade by blade, engine by engine, sortie by sortie. Snow still clung to the edges of the airfields when the first P-51 Mustangs received their paddle blade conversions. The Mustang was already a thoroughbred, long-range, nimble, and fast. But at high altitude, even its performance was limited by the slender blade propeller it had inherited from an earlier era. When the paddle blade was bolted to the Rolls-Royce Merlin engine, something extraordinary happened. The aircraft's acceleration improved noticeably, its climb rate soared, and its top speed jumped. At high altitudes, where bombers flew and where Luftwaffe interceptors waited, the Mustang now reigned supreme. On February 20th, 1944, the Allies launched Operation Argument, better known as Big Week. It was the largest coordinated bombing campaign of the war up to that point. Thousands of bombers, escorted by Thunderbolts and Mustangs, poured into German airspace. The Luftwaffe met them in force. Dozens of Bf-109s and FW-190s clawed for altitude, preparing to pounce. But as they climbed, the American escorts were already there. The new paddle blade propellers allowed fighters to maintain speed even as they climbed steeply. Instead of arriving fragmented or late to the fight, escort formations stayed tight and cohesive. Luftwaffe pilots expecting sluggish Thunderbolts and outpaced Mustangs found themselves facing fast, aggressive opponents who could now fight on equal footing, or better. The engagements during Big Week were brutal. High above the industrial cities of Germany, contrails tangled in the sky like white scars. Fighter groups clashed in swirling dogfights at altitudes that once favored the defenders. German pilots could no longer rely on simply diving away to escape. The paddle blade propellers gave American fighters the thrust to stay with them. P-51s and P-47s began pursuing German interceptors over their own airfields. For the first time, Allied fighters dictated the terms of the air battle. The Luftwaffe's defensive rhythm, built on altitude advantage and speed, began to fracture. One Luftwaffe report from early March 1944 captured the change bluntly. The American fighters now climb like our own. Escape is increasingly difficult. Behind every one of those fast-climbing, fast-diving escorts was the same quiet innovation. A broad, efficient blade that turned raw horsepower into relentless speed. In the weeks that followed Big Week, the Luftwaffe lost hundreds of aircraft. But the losses weren't just in metal. They were in momentum, in initiative, in control of the skies. The paddle blade propeller had done more than make planes faster. It had helped rewrite the tempo of the air war over Europe. By the spring of 1944, the results were impossible to ignore. The new propellers had transformed the performance of America's frontline fighters. What had once been incremental gains became a leap forward in combat capability. For the P-47 Thunderbolt, climb rate increased by nearly 500 feet per minute, and top speed at altitude rose by over 25 to 30 miles per hour. The P-51 Mustang achieved even greater gains, especially above 20,000 feet. The Comte's paddle blade propeller didn't just make these planes faster, it allowed them to sustain that speed over the long, punishing range of deep penetration missions into Germany. Bomber crews began to notice the change. Where once Thunderbolts lagged behind, now they soared alongside, weaving through bomber formations as sentinels of polished aluminum. They met German interceptors on equal terms, breaking attacks before they reached the bombers. The Luftwaffe's losses began to climb, not gradually, but steeply. In just a few months, the US 8th Air Force saw bomber losses fall dramatically. Escort fighters equipped with paddle blades were returning from missions with higher kill counts and fewer mechanical failures. Reports from combat groups described the improvement as remarkable stability and power at altitude, but numbers told only part of the story. The psychological shift among airmen was profound. Pilots who had once fought with the quiet anxiety of technological inferiority now flew with confidence. They could dive, chase, and climb with assurance. They were no longer holding the line. They were pushing it forward. Meanwhile, Hamilton's Standard ramped up production to unprecedented levels. By mid-1944, nearly every frontline US fighter in Europe, P-47s, P-51s, and even some P-38 Lightnings, had been fitted with the new blades. Caldwell's crazy design had become standard issue. In combat reports and pilot memoirs, it was rarely given headlines. There were no propaganda posters or newspaper stories celebrating it. But in the quiet language of engineering, it was revolutionary. Every mission flown, every bomber saved, every enemy intercepted, bore silent witness to its impact. The Allies now controlled the air, not just with numbers, but with innovation. And innovation, as history would soon show, was about to carry them all the way to victory. By the summer of 1944, the transformation was complete. Paddle blade propellers were no longer a novel experiment. They were the beating heart of Allied air power. Every new Thunderbolt and Mustang rolling off the line bore the distinctive broad blades that had once drawn skepticism. The strategic consequences were immense. Escort fighters could now accompany bombers all the way into the industrial core of the Reich and back. Luftwaffe interception windows, once wide and decisive, narrowed sharply. German pilots no longer enjoyed the luxury of choosing when and where to engage. Instead, they found themselves reacting to an enemy that could outclimb, outpace, and outlast them. This shift directly underpinned the success of Operation Argument and the broader Allied bombing campaign. With long-range, high-speed escorts dominating the skies, bomber losses plummeted, and the Luftwaffe was forced into an attritional air war it could not sustain. Between February and June 1944, German fighter strength declined sharply. Each lost aircraft was more than metal. It was a trained pilot, an experienced wingman, a dwindling resource that Germany could no longer replace at scale. The paddle blade propeller also set the stage for the air superiority that enabled D-Day. In June 1944, as Allied forces stormed the beaches of Normandy, fighter bombers and escorts swept the skies clear. The Luftwaffe's ability to mount coordinated, large-scale opposition had been broken months earlier, in no small part because its pilots could no longer escape or dictate engagements as they once had. Even after the war, aviation engineers recognized this development as a turning point. It wasn't as dramatic as the arrival of the jet engine, nor as visible as radar or the atomic bomb. But its impact on the outcome of the air war was profound. It was a textbook case of how a single, well-executed engineering breakthrough could cascade through tactics, strategy, and ultimately history itself. For Frank Caldwell, it was vindication. The man who had once been told his idea looked like something off a tugboat had helped give the Allies their decisive aerial edge. His paddle-blade propeller design earned him the Collier Trophy, one of aviation's highest honors. A simple change in shape had changed the shape of a war. History often remembers the loud things, the thunder of engines, the clash of armies, the roar of victory. But sometimes, the most decisive shifts come from quiet ideas, from the hands of engineers who stare at a problem long enough to see what others overlook. The paddle-blade propeller didn't look heroic. It wasn't glamorous. It didn't make headlines or inspire wartime posters. But in 1944, it changed the air war over Europe. By unlocking the full power of the engines already sitting on American fighters, it gave the Allies something far more precious than raw speed. It gave them control. It erased the Luftwaffe's altitude advantage. It kept bombers alive. It allowed Thunderbolts and Mustangs to dominate skies once ruled by their enemy. And it did so not with new weapons or more firepower, but with a smarter use of what already existed. Frank Caldwell's crazy idea was never just about a blade. It was about understanding that innovation isn't always invention. Sometimes it's transformation. That broader, thicker, stronger propeller became a silent ally in thousands of missions. Its shape cut through the air, but its impact cut through the course of the war. And when the contrails faded, and the skies over Europe grew quiet again, history had already turned, one blade at a time. One small change changed everything. If you want more untold stories of Tubby-Point innovation, the silent breakthroughs behind the loud victories, subscribe and join us on the next mission. History is waiting.